a visitor from beyond our solar system just spoke. For the first time in human history, we've received a clear, undeniable signal from something that doesn't belong to our cosmic neighbourhood. Not a whisper from a distant star system merely inferred from light. Not an echo from a planet billions of miles away within our sun's gravitational embrace. No, this was a direct active transmission from an object that wandered into our solar system from the vast empty void between the stars. This object, designated 3I Atlas, 3I, signifying it as the third interstellar visitor ever confirmed by astronomers, has been silent throughout its immense journey. Throughout its lonely pilgrimage across light years of frigid darkness, it remained a mute, icy wanderer. So why, after eons of cosmic silence, is it suddenly speaking now? And how is such a thing even possible? Let me be absolutely clear about something right from the start. This isn't science fiction conjured from human imagination. This isn't mere speculation wrapped in hopeful anticipation of first contact. This is rigorously verified data collected and meticulously analysed by one of the most advanced radio telescope arrays on Earth. It was processed by a global network of astronomers who have spent their entire careers distinguishing the subtle, complex symphony of cosmic noise from genuine interpretable phenomena. The signal is real. The source is unequivocally confirmed. And yet everything about this discovery challenges what we thought we knew about visitors from beyond our solar system, forcing us to re-evaluate our place in a far more dynamic and interconnected galaxy. You're probably thinking what almost everyone thought when the news first broke: alien probe, extraterrestrial technology. The moment humanity has been waiting for since we first looked up at the stars and wondered if we are truly alone in this boundless universe. I understand that primal impulse. I felt it too. It's a natural human reaction to the unknown, a deep-seated hope for connection. But here is where the story truly becomes more fascinating, more profound, and ultimately more awe-inspiring than any simple alien narrative could ever be. Because the truth about this signal, the actual scientific explanation, reveals something fundamental and utterly breathtaking about the universe that we are only just beginning to truly understand. And before I tell you what that truth is, you need to understand why this discovery is so unprecedented, so paradigm-shifting, that it is already forcing scientists to rewrite sections of their textbooks and reimagine the cosmic landscape. 3I Atlas entered our solar system not just as a mystery, but as a living enigma. Unlike the planets, asteroids and comets that were born alongside our Sun some 4.6 billion years ago, forged from the same primordial cloud of gas and dust, this object came from somewhere else entirely. It travelled through the crushing darkness and near-perfect vacuum between stars for potentially millions, even billions of years, a journey almost incomprehensible in human terms. Imagine a single grain of sand preserved for geological epochs finally drifting into your backyard. That's the scale of this cosmic encounter. For millennia, it was a solitary wanderer propelled by the faint gravitational whispers of the galactic spiral arms before the sun's immense gravity gently subtly pulled it into our cosmic neighbourhood, bending its trajectory just enough for us to notice. When astronomers first identified its hyperbolic trajectory, a path that clearly indicated it was not gravitationally bound to our sun but merely passing through, and confirmed it as an interstellar visitor, the scientific community held its collective breath. Because the very first interstellar object we ever detected, Oumuamua, sparked years of intense debate and wild speculation that to this day hasn't been fully resolved. Some scientists argued it was just an unusual comet, perhaps one made of exotic ices like solid hydrogen. Others suggested its peculiar acceleration patterns and its highly elongated shape were inconsistent with any known natural objects, leaving a lingering, tantalizing suspicion of artificiality. The mystery of Oumuamua taught us a crucial lesson. Interstellar visitors don't always play by the rules we've established studying objects born in our own solar system. We had to prepare for the unexpected. So when 3I Atlas appeared on our cosmic radar, astronomers watched it with an intense scrutiny, that bordered on obsession, deploying every tool in their arsenal to understand its true nature before it slipped away forever into the galactic night. Multiple optical telescopes from Hawaii to Chile tracked its precise trajectory like cosmic air traffic controllers. Spectrometers analysed the faint light reflecting off its surface, searching for chemical signatures. Observatories monitored its brightness as it tumbled silently through space, hoping for clues to its rotation and composition. And throughout all of this, for months, there was nothing but silence. No radio emissions, no unusual energy signatures, just reflected sunlight and the normal characteristics you'd expect from a colossal dirty snowball of ancient rock and ice wandering through the frigid void. Until October 2025. That's when Meerkat, the incredibly sophisticated radio telescope array nestled in the remote Karoo Desert of South Africa, detected something that made astronomers stop, lean in, and stare at their monitors in utter disbelief. A clear, undeniable radio signal at a very specific frequency emanating directly from 3I Atlas. This wasn't random noise. This wasn't terrestrial interference. This was a clear, distinct emission at an 18-centimetre wavelength, the unmistakable signature frequency of hydroxyl radicals, specifically the OH molecules that form when water breaks apart under the intense, energetic radiation of the sun. Now here's where your mind might instinctively race ahead of the facts drawn by the siren song of science fiction. A signal from an interstellar object, a voice from the deep void, sounds exactly like the setup for first contact, doesn't it? But pause for a moment and consider what makes this discovery so much more intriguing, so much more profound than a simple alien probe narrative. This signal tells us that 3I Atlas is alive in a way we have never before witnessed in an interstellar visitor. Not alive with biology or technology, but vibrantly alive with chemistry, alive with transformation, alive with internal processes that are revealing the fundamental composition and the ancient, untold history of an object that formed in an entirely different stellar system than our own. The hydroxyl emission detected by Meerkat, this specific 18-centimetre wavelength, indicates with scientific certainty that 3I Atlas is actively outgassing. Water ice locked within its dense frozen structure for potentially millions or even billions of years, a cosmic time capsule, is now sublimating. It's transforming directly from its solid icy state into a gas bypassing the liquid phase altogether as the object approaches the sun's intense heat during its perihelion passage, its closest point to our star. And when that water vapour breaks apart under the brutal onslaught of solar ultraviolet radiation, it creates precisely these hydroxyl radicals. These OH molecules then emit at a very specific universal radio frequency that our powerful telescopes can detect from millions of miles away. This then is the signal. This is the voice of 3I Atlas. Not a coded message, not a deliberate beacon designed by an alien intelligence, but the natural radio signature of an ancient comet from another star system, revealing its innermost chemical secrets for the very first time. It is the universe speaking to us in its most fundamental language, the language of physics and chemistry. But why now? Why did 3I Atlas remain utterly radio silent throughout its entire approach, only to suddenly emit this distinct signal just as it reached the inner solar system? The answer lies in understanding the intimate relationship between comets and the sun, a celestial dance driven by heat and light. As 3I Atlas travelled through the frigid, cold outer reaches of our solar system, far beyond the orbit of Jupiter, it was essentially dormant. At those immense distances, solar radiation is simply too weak to sublimate the volatile ices locked within the comet's nucleus. It was a frozen, inert relic, a deep space sleeper. But as its orbital trajectory brought it closer and closer to the sun, crossing the critical threshold where solar heating becomes intense enough to drive these powerful chemical reactions, 3I Atlas effectively woke up. The outgassing began in earnest. The water molecules, slowly liberated from their icy prisons, started their journey into the vacuum. The hydroxyl radicals formed in increasing numbers as sunlight tore them apart. And for the first time in eons, this traveller from beyond our stars started broadcasting its presence, its very existence, to anyone listening with the right equipment. This is the moment where I need you to truly absorb the profound significance of what's happening here. We are detecting in real time the chemical transformation of matter that originated in an entirely different stellar system. The water molecules breaking apart to create this radio signal did not form around our sun. They crystallized around a different star in a swirling protoplanetary disk that gave birth to planets and comets we will never see directly in a system that might be hundreds of light years from Earth. And now that ancient alien water is revealing itself to us through the universal, unchanging language of physics and chemistry, a language understood across the cosmos. This detection confirms what many astronomers suspected but couldn't definitively prove. Until now, 3I Atlas is almost certainly an interstellar comet. Not an asteroid, not a rogue piece of planetary debris, but a primordial mixture of ice and rock that has preserved within its frozen heart the chemical fingerprint of its birth star system. And that fingerprint, that cosmic ID card, is now being transmitted to Earth in the form of these hydroxyl radio emissions, which tell us unequivocally that this object contains significant amounts of water. Water, one of the most fundamental molecules in the universe, a key ingredient for life as we know it, a ubiquitous solvent and medium. This means the building blocks for life, or at least the foundational chemistry, are not unique to our solar system. They are widely distributed throughout the galaxy, carried by these silent icy messengers. I want you to think about the incredible odds, the sheer cosmic serendipity of this moment. In all of human history, with all our telescopes and scientific ingenuity, we have only confirmed 3 interstellar objects passing through our solar system. 3 visitors from the vast cosmic ocean that surrounds us. And now with 3I Atlas, we're not just watching from a distance observing its light, we're actively listening. We're hearing its chemical voice extracting its secrets in ways that simply weren't possible with previous more fleeting visitors. This is the first time we have ever detected a radio signal from an interstellar comet, and that first time that groundbreaking moment is happening right now in your lifetime. During this brief, precious window when 3I Atlas is close enough to the Sun to activate its icy core and close enough to Earth for our sophisticated telescopes to capture its emissions, the global scientific community is buzzing with activity. Research papers are being hastily written and peer-reviewed. Data is being analysed from multiple observation platforms across the electromagnetic spectrum. Because this signal represents more than just a single detection, it represents the validation of an entirely new method, a new frontier in astrochemistry that can be applied to future interstellar visitors. It proves beyond a doubt that radio astronomy can powerfully reveal the chemical composition and active processes of objects from beyond our solar system in ways that optical observation alone simply cannot achieve. And in doing so, it opens a brand new chapter in our ability to study and understand the universe beyond the familiar confines of our immediate cosmic neighbourhood. This isn't just about an object, it's about a revolutionary new way of understanding the cosmos. But I see the question in your eyes. I hear the calm, skeptical voice in the back of your mind saying, how do we know this is really just a natural comet? How do we know there isn't something more to this signal? Something artificial? Something intentional? And that, my friend, is exactly the right question to ask. That is the critical thinking, the scientific skepticism that separates genuine investigation from blind acceptance or wishful thinking. So let me take you deeper into what the data actually shows, what the rigorous science really says, and why this natural explanation is in its own way far more extraordinary and profoundly beautiful than any artificial alternative could ever be. Because truly, understanding the truth about this signal and embracing the awe it evokes requires us to explore the intricate, elegant science behind hydroxyl emissions, the nuanced nature of cometary outgassing, and the specific cosmic conditions that allow us to detect these phenomena from objects travelling through our solar system. And that journey into understanding starts with unpacking the fundamental physics and chemistry that make this signal possible in the first place, a universal language of matter and energy. To understand what 3i Atlas is truly telling us, you need to understand the language it's speaking, and that language is not a code. It is written in the precise physics of molecular bonds, the predictable behaviour of ice under radiation, and the very specific radio frequencies that hydroxyl radicals emit when they form in the harsh, unforgiving environment of space. This isn't abstract theory or conjecture. This is measurable, predictable science that we've confirmed thousands of times over through decades of studying comets born right here in our own solar system. The profound difference, the revolutionary aspect, is that we're now applying this deep, confirmed knowledge to an object that came from somewhere else entirely, a true alien in the most scientific sense of the word. Let me walk you through the precise sequence of events that unfolds when any comet, approaches the Sun. Deep within the comet's nucleus, locked in a frozen matrix of rock and ice, are molecules of water, simple H2O. 2 hydrogen atoms bonded to 1 oxygen atom. At the unimaginably frigid temperatures of the outer solar system, far from any star, these molecules remain solid, trapped in crystalline structures that can persist unchanged for billions of years. The comet is dormant, a flying iceberg preserving the chemical conditions of its birth environment, a relic frozen in time. But as the comet's elliptical orbit, or in 3i Atlas's case, its hyperbolic trajectory brings it closer to the Sun, everything begins to change. Solar radiation, particularly the energetic ultraviolet light, begins to gently, then intensely heat the surface of the nucleus. At a certain threshold, roughly around the orbit of Jupiter, though varying based on the comet's specific composition and dark albedo, the ice begins to sublimate. Crucially, it does not melt. Sublimate. That's a vital distinction. In the near-perfect vacuum of space, solid ice transforms directly into gas without ever passing through a liquid phase. These liberated water molecules break free from their solid matrix, forming a rapidly expanding cloud that streams away from the nucleus, creating what we see as the comet's coma, the fuzzy glowing envelope of gas and dust surrounding its solid core. But here's where the chemistry gets truly fascinating and provides our signal. Once those water molecules escape into the vacuum of space, they are immediately exposed to an onslaught of intense solar radiation that wasn't strong enough to penetrate and reach them while they were buried deep within the nucleus. Ultraviolet photons from the Sun strike the water molecules and break them apart in a process called photodissociation. The delicate bonds holding the hydrogen and oxygen atoms together literally snap, and when they do, they create hydroxyl radicals, molecules that are highly reactive, chemically unstable, and possess a very specific quantum mechanical property that makes them uniquely detectable across vast interstellar distances. Hydroxyl radicals emit radio waves at a precise and utterly consistent frequency, 665 402 MHz MHz, which corresponds to a wavelength of about 18 centimeters. This emission happens because of the arcane yet beautiful rules of quantum mechanics. The OH molecule can exist in different energy states, and when it transitions from a higher energy state to a lower one, it releases the excess energy as a photon, a tiny packet of light, at that exact specific frequency. This isn't random. This is as consistent and predictable as gravity itself. Every hydroxyl radical in the universe, whether it forms near Earth or in a comet from another star system, emits at precisely the same frequency. It is a universal chemical signature, a cosmic barcode that radio astronomers can detect with extraordinary precision. This precisely is what Meerkat detected from 3i Atlas. The radio signal at 18 centimeters isn't mysterious. It isn't unexplained. It is the direct measurable consequence of water ice sublimating from the comet's nucleus and breaking apart under solar radiation to form hydroxyl radicals that then emit at their characteristic frequency. We've seen this exact signature from hundreds of comets in our own solar system, confirmed and studied for decades. What makes the 3i Atlas detection so special isn't the nature of the signal, it's the source. For the very first time, we're detecting this unmistakable signature from water that originated far beyond our sun's gravitational and chemical influence, water forged in the crucible of another star. Now you might wonder if this is such a common process. Why didn't we detect this signal earlier, especially if 3I Atlas has been in our solar system for months? The answer lies in understanding the dynamic relationship between solar distance and outgassing intensity. Comets don't outgas at a constant uniform rate. The farther they are from the sun, the weaker the solar heating, and thus the weaker the outgassing. As 3I Atlas continued its inward plunge approaching perihelion, its closest point to the sun, which occurred in late October 2025, the heating intensified dramatically. The sublimation rate of water ice increased exponentially. More water molecules escaped the nucleus. More hydroxyl radicals formed in the expanding coma. And critically, the collective radio emission from these trillions of OH molecules became strong enough for powerful telescopes like Meerkat to detect it above the faint background noise of space. The timing of the detection itself also tells us something profound about the composition of 3I Atlas. Not all comets produce strong hydroxyl emissions. The intensity depends significantly on the total amount of water ice locked within the nucleus, the specific structure of the ice matrix, and how efficiently the comet releases gas as it heats up. The fact that Meerkat detected such a clear and robust signal indicates that 3I Atlas contains substantial amounts of water ice, comparable to what we observe in many long-period comets, originating from our own solar system's Oort cloud. This similarity is itself remarkable. It suggests that the fundamental conditions that formed comets in our solar system, the precise temperatures and chemical processes that locked water into icy nuclei, also occurred in the distant stellar system where 3I Atlas originated. It speaks to a universality of planet formation, a cosmic template replicated across the galaxy. But the detection goes beyond just confirming water content. The hydroxyl emission data, precisely calibrated by years of previous research, allows astronomers to calculate the comet's outgassing rate, the staggering amount of water being lost per second as the comet heats. Early estimates from the Meerkat data suggest that 3I Atlas was releasing water at a rate consistent with a nucleus several kilometers in diameter, a typical size for many long-period comets we know. This invaluable measurement helps to constrain the actual size and mass of the object details that are notoriously difficult to determine from optical observations alone, because the overwhelming brightness of the coma can often mask the faint reflected light from the solid nucleus itself. The radio detection also provides tantalizing clues about the distribution of ice within the nucleus. If 3I Atlas were merely a solid uniform ice ball, we would expect very different and more predictable outgassing patterns than what we observed. Instead, the data suggests a more heterogeneous, perhaps fractured structure, with ice mixed unevenly among rocky material, creating a porous matrix that allows gas to escape through cracks and channels as the surface heats. This structure beautifully matches theoretical models of how comets form in swirling protoplanetary disks where ice grains and rocky dust clump together through countless gentle collisions over millions of years, building up layers that preserve the chemical diversity of the disk environment. What's particularly intriguing is comparing the hydroxyl emissions from 3I Atlas to those from comets native to our own solar system. Radio astronomers can measure subtle differences in the emission spectrum, the precise shape and width of the radio line, that reveal critical information about the physical conditions in the coma, such as its temperature density and the expansion velocity of the gas. Early analysis suggests that the hydroxyl emission from 3I Atlas is remarkably similar to what we see from comets born around our sun. The gas is expanding at comparable speeds. The emission profile matches the expected shape for a comet at that solar distance. Everything about the signal screams normal comet physics, just applied to an object with an utterly extraordinary origin story. This is where the elegance and predictive power of science truly shine. We have a robust scientific framework built over decades of studying comets in our own solar system that predicts exactly what a radio emission from outgassing water should look like for a comet of a given size at a given distance from the Sun. And when we point our most sensitive radio telescopes at 3i Atlas, the data fits that framework beautifully, almost perfectly. There are no anomalies in the emission spectrum, no unexpected frequencies, no bizarre modulations or repeating patterns that would suggest anything other than natural outgassing and photodissociation. The signal is precisely what physics and chemistry predict it should be. But here's what makes this even more compelling and definitively separates it from any artificial explanation. Radio astronomy isn't just passive observation. By continuously detecting hydroxyl emissions, astronomers can track how the outgassing evolves over time as the comet's distance from the Sun changes. After perihelion, as 3i Atlas began its journey back out into the cold, distant outer solar system, the outgassing inevitably declined. The hydroxyl emission progressively weakened following the predicted mathematical curve, and eventually, as the comet crosses back beyond the threshold, where solar heating is insufficient to sublimate its volatile ice, the signal will disappear entirely. The comet will fall silent again, returning to its dormant state, a frozen ghost receding into the darkness. That precisely predictable pattern, intensifying as it approaches the Sun, then steadily fading as it recedes, is already being observed with emission intensity tracking the expected curve based on solar distance. This temporal evolution of the signal is perhaps the strongest, most undeniable evidence that what we're detecting is natural cometary behaviour, rather than any artificial source. An artificial transmitter, whether alien or human-made, would have entirely different characteristics. It wouldn't naturally intensify in perfect correlation with solar heating, and then fade in perfect correlation with solar cooling. It wouldn't emit at the exact frequency universally associated with hydroxyl transitions, and it certainly wouldn't show the spectral characteristics of expanding gas in a comet coma. The signal fits the comet model so perfectly, so elegantly, that invoking any alternative explanation requires ignoring the simplest, most consistent interpretation of the overwhelming data. Yet I know there's still a part of your mind that, despite the scientific rigour, wants to hold on to the possibility of something more, something truly unprecedented, something alien. And that's not wrong. That innate human curiosity is precisely what drives science forward. But satisfying that curiosity responsibly means looking at all the evidence, not just the parts that might confirm what we want to believe. So let's confront the alien probe hypothesis directly. Let's examine with scientific precision what the data would look like if 3i Atlas were artificial, and why the hydroxyl signal we're detecting doesn't match that profile at all. Because understanding what something is often requires understanding what it isn't. And that means honestly evaluating the alternatives with a calm, rational skepticism before accepting the conclusion that best fits the totality of the evidence. I need to address the elephant in the room, the headline that spread across social media faster than the actual science, the speculation that lit up comment sections and conspiracy forums the moment news broke about a signal from 3i Atlas, alien probe extraterrestrial beacon proof that we're being watched. You saw those headlines. You felt that surge of excitement, that unique thrill of possibility. And you're wondering if there's any truth behind them, if maybe the scientists are missing something obvious, or even worse, covering up something profound. So let me walk you through exactly why the alien hypothesis doesn't just fail to explain the data, it actively contradicts what we're observing. First, let's establish what an artificial signal would actually look like based on decades of SETI research and our understanding of communication technology. If 3i Atlas were a probe designed by an extraterrestrial intelligence, whether it was actively transmitting dormant and accidentally leaking radiation, or even designed to mimic a natural object, the radio emissions would have fundamentally different characteristics than what we're detecting. Artificial signals, especially those designed for communication or navigation, tend to be narrowband. This means they concentrate their energy at a very specific tight frequency like a laser beam to maximize signal strength and reduce noise over vast distances. Natural emissions, such as those from hydroxyl radicals by contrast, show a characteristic spectral profile with specific line shapes that are determined by the physical conditions, temperature, density, velocity of the gas cloud. The meerkat detection shows exactly that natural broad spectral profile, with no signs of narrowband compression. Moreover, an artificial transmitter would almost certainly show stability, or more likely modulation patterns that reflect its designed purpose. Communication signals often exhibit timing patterns, repeating sequences, or information encoding that manifests as variations in intensity or frequency over time. Navigation beacons might show periodic pulses or sweeps across frequencies, but the hydroxyl emission from 3I Atlas shows none of these characteristics. Its intensity varies smoothly and predictably, with solar distance exactly as we'd predict for outgassing that increases near perihelion and decreases as the comet recedes. There's no modulation, no periodicity beyond what you might expect from the comet's rotation, affecting which parts of the nucleus are illuminated. No discernible patterns that suggest intentional encoding of information. It's just the steady chemically driven hum of evaporating water. The specific frequency itself is another telling clue. Why would an artificial transmitter broadcast at exactly 1665.402 MHz the precise unvarying frequency of hydroxyl emission? That frequency isn't special for communications. It's not a universal beacon wavelength, like, for instance, the 1420 MHz hydrogen line, which has long been proposed as a logical universal frequency for interstellar communication, because it's based on a fundamental physical constant. But hydroxyl at 18 centimeters, that is nature's frequency, the unavoidable spectroscopic signature of a specific chemical process, not an engineer's design choice. It would be akin to finding a rustling in a forest and claiming it's a coded alien message when it's just the wind moving leaves. Some have argued that the timing of the signal's appearance is suspicious, that 3I Atlas remained silent until it got close to Earth, suggesting it might be responding to our presence or our transmissions. But this argument crumbles entirely when you understand the fundamental physics of comets. The signal didn't appear when 3I Atlas got close to Earth. It appeared when 3I Atlas got close to the Sun. This is precisely when outgassing physics predicts hydroxyl emissions should become detectable due to increased solar heating. The correlation isn't with Earth's position but with solar distance. And that correlation is perfect following the well-established mathematical relationship between solar heating and the rate of sublimation that we've confirmed with countless solar system comets. Let's also address the underlying assumption that seems to fuel much of the speculation, that an interstellar object must be artificial simply because it came from another star system. This assumption reveals a deep-seated bias in how we tend to think about interstellar space. We often imagine the void between stars as utterly empty, as if objects either orbit stars or don't exist at all. But the reality is that space is teeming with rogue objects, planets violently ejected from their birth systems, comets kicked out by chaotic gravitational interactions, asteroids freed by stellar encounters all drifting. Theoretical simulations backed by observations suggest there could be trillions of interstellar objects in our galaxy alone, vastly outnumbering the stars themselves. The fact that one occasionally passes through our solar system isn't suspicious or extraordinary. It's statistically inevitable, a cosmic certainty. And here's the crucial point that often gets lost in the fervour of speculation. We've now studied 3I Atlas with multiple instruments using multiple techniques across the electromagnetic spectrum. Optical telescopes have analysed the sunlight, reflecting off its surface, revealing a spectrum entirely consistent with rocky and icy material strikingly similar to solar system comets. Colour measurements show the reddish tint typical of organic-rich surfaces that have been exposed to cosmic radiation over unimaginably long timescales. The morphology of its coma and tail perfectly matches what we see in natural outgassing, with dust and gas following trajectories determined purely by solar radiation pressure and the comet's motion through space. Every single measurement from every single instrument points to the same consistent conclusion: a natural comet. Some researchers, and I want to be fair here, have rightly suggested that we should always keep an open mind about all possibilities until we have definitive proof. And in principle, that's sound scientific practice, the very bedrock of discovery. But keeping an open mind doesn't mean treating all hypotheses as equally likely, when the overwhelming evidence clearly favours one explanation over all others. The burden of proof in science always lies with those proposing extraordinary claims, and the claim that 3I Atlas is artificial is by any measure an extraordinary claim. To justify that claim, you'd need to explain logically and without contradiction why the object looks like a comet, acts like a comet, emits signals like a comet, and perfectly matches all the predictions of comet physics if it's actually an alien probe. That requires adding multiple layers of convoluted, unsupported assumptions that the natural explanation simply doesn't need. Consider the principle of parsimony, often called Occam's razor. When multiple explanations fit the observations, the one requiring the fewest unsupported assumptions is most likely correct. The natural comet explanation requires only the well-understood laws of physics and chemistry, which we've already confirmed through decades of studying solar system comets. The artificial probe explanation requires assuming that extraterrestrial civilizations exist, assuming they've developed interstellar travel, assuming they've sent probes to our solar system, assuming one of those probes happens to look and act exactly like a natural comet, and assuming the hydroxyl emission we're detecting is somehow mimicry or coincidence rather than actual outgassing. Each of those assumptions is an additional unsupported layer that makes the hypothesis exponentially less likely. Now I want to acknowledge something important. The search for extraterrestrial intelligence SETI is legitimate, rigorous science. SETI researchers have spent decades developing precise, rigorous methods to distinguish artificial signals from natural phenomena, and those methods are being applied directly to interstellar objects. When Oumuamua passed through our solar system, the Breakthrough Listen project, a privately funded SETI initiative, targeted it with some of the world's most powerful radio telescopes specifically to search for artificial transmissions. They found nothing. No narrowband signals, no modulated transmissions, nothing that couldn't be explained by natural processes or background noise. Similar monitoring was conducted on the second interstellar object 2I Borisov with the same null result. And now, with 3I Atlas, the signal we're detecting is clearly an unambiguously natural hydroxyl emission, not an artificial transmission. The scientific consensus on 3I Atlas is remarkably strong. Researchers from multiple institutions using different telescopes and different analysis methods have all reached the same conclusion. This is an interstellar comet undergoing normal, albeit intense, outgassing as it passes through the inner solar system. That consensus isn't the result of closed-mindedness or an unwillingness to consider alternatives. It's the inevitable result of overwhelming, consistent evidence pointing in the same direction. And in science, consensus built on robust evidence is how we distinguish reliable knowledge from enticing speculation. But here's what I find most fascinating about the alien probe speculation. It actually makes 3I Atlas less interesting than what it truly is. An artificial probe, while profoundly significant, would tell us primarily about the civilization that built it. But a natural interstellar comet that tells us about the conditions in other stellar systems. It tells us about the chemical processes that form planetary systems across the entire galaxy. It tells us about the age and evolution of objects that travelled through interstellar space for timescales we can barely comprehend, acting as an ancient, unwritten chronicle of cosmic history. The truth about 3I Atlas is that it's a messenger not carrying an intentional message from alien engineers, but carrying priceless chemical information encoded in its very structure about the distant place and time of its formation. And that brings us to the question that matters most. If 3I Atlas is a natural comet, Why does it seem so unusual? Why does it spark so much speculation at all? Every comet, like every snowflake, has its quirks, its peculiarities that make it slightly different from every other comet we've observed. But 3I Atlas stands out even among a population known for its diversity. And those unusual traits are precisely what fuel speculation, what make headlines, what convince some people that there must be more to this story than scientists are telling us. So let's examine those traits directly one by one and understand what they actually reveal about this truly extraordinary traveller from beyond our solar system. The first thing that instantly caught astronomers' attention was 3I Atlas's speed. When the object was first tracked, its velocity relative to the Sun immediately flagged it as hyperbolic, meaning its trajectory wasn't bound to our solar system. It wasn't in an elliptical orbit that would eventually bring it back. It was merely passing through, following a path that would carry it back out into interstellar space, never to return, and even accounting for the Sun's immense gravity, which speeds up any object as it falls inward and slows it as it climbs back out. 3I Atlas retained a significant excess velocity, indicating it came from outside. Estimates put its original interstellar velocity at somewhere around 14 to 17 kilometers per second, fast enough to traverse the distance from Earth to the Moon in about half an hour. But here's what you need to understand, that speed isn't evidence of propulsion or artificial control, it's evidence of origin and galactic motion. Objects in interstellar space don't just sit still suspended, they orbit the galactic centre, along with all the stars in the Milky Way moving at hundreds of kilometers per second relative to distant galaxies. But relative to each other, stars and interstellar objects in the same local region of the galaxy. They move at a range of velocities typically between 10 and 30 kilometers per second. 3 Atlas's observed speed fits perfectly within that natural range. It's exactly what you'd expect for an object drifting through interstellar space until it happened by pure chance to encounter our solar system's gravitational influence. It's the speed of a galactic vagabond, not an engineered spacecraft. The trajectory itself is also profoundly revealing. By meticulously backtracking the path of 3I Atlas through space and accounting for its velocity, astronomers can estimate the general direction from which it came. The calculations suggest it originated from somewhere in the direction of the constellation Draco, from a region that doesn't correspond to any nearby stars that we know of. This tells us that 3I Atlas has likely been travelling through interstellar space for an immense period, potentially millions of years, long enough that the star system where it formed has moved to a completely different position in the galaxy due to galactic rotation. This object is truly ancient, a relic from a stellar system that might not even exist anymore in any recognisable form, its parent star long since faded or moved on. Another feature that's garnered attention is the comet's composition, particularly its unusually high carbon dioxide content. Spectroscopic observations during the months leading up to perihelion detected strong carbon dioxide emissions, indicating that the nucleus contained substantial amounts of CO2 ice, along with its water ice. In our own solar system, carbon dioxide is common in comets, but the ratio observed in 3I Atlas appears somewhat higher than typical for our local comets. Some have pointed to this as potential evidence of exotic origin or unusual formation conditions. But the reality is that we don't yet have a large enough sample size of interstellar comets to truly know what's typical and what's unusual for objects formed around other stars. The high CO2 content actually tells us something scientifically invaluable. Carbon dioxide is more volatile than water, meaning it sublimates at lower temperatures and at greater distances from the Sun. The fact that 3I Atlas still retains significant carbon dioxide after potentially millions of years in the comparatively warmer inner solar system suggests it has been cold enough throughout its entire interstellar journey to preserve these highly volatile ices. This preservation gives us a pristine snapshot of the comet's original composition, less altered by repeated heating and outgassing than comets that have made multiple passes through the inner solar system. In a very real sense, 3I Atlas is more pristine, more representative of the conditions in its birth environment than many of the comets we've studied that have been modified by repeated solar encounters. It's a truly ancient, well-preserved sample. Then there's the brightness behaviour, which has been described as erratic and difficult to predict. In the months leading up to perihelion 3I Atlas showed unexpected surges in brightness, moments when it suddenly became more visible in telescopes before fading again. These outbursts are actually quite common in comets, and are usually associated with sudden localised releases of gas and dust from the nucleus, possibly from the collapse of fragile surface structures, or the exposure of fresh supervolatile ice as surface layers sublimate away. But the timing and intensity of 3I Atlas's outbursts didn't follow patterns that astronomers could easily predict based on its distance from the Sun alone. This unpredictability has certainly led to speculation about internal activity, about structural features, or composition variations within the nucleus that cause uneven outgassing. And that speculation is probably correct, but there's nothing artificial about it. Comet nuclei are far from uniform. They are heterogeneous mixtures of ice rock and complex organic material that accumulated over millions of years in chaotic protoplanetary disks. Some regions might be ice-rich, others rock-rich. Some areas might have more volatile ices like carbon monoxide or nitrogen, which can sublimate explosively at certain temperatures. As the comet rotates, different areas are exposed to sunlight, creating variations in outgassing that manifest as the brightness changes we observe from Earth. It's like a geological event on a cosmic scale, a natural eruption of internal energy. One of the most visually striking features of 3I Atlas has been its anti-tail, a phenomenon where the tail appears to point toward the Sun rather than away from it. This sounds impossible at first glance, since comet tails form when solar radiation and the solar wind push gas and dust away from the nucleus. But anti-tails are actually a well-understood optical illusion. They occur when Earth's position relative to the comet places us in the plane of the comet's orbit, allowing us to see the broad, flat dust trail that the comet leaves behind along its entire orbital path. From our specific perspective, this expansive dust trail projects both ahead and behind the nucleus, creating the appearance of a tail pointing in both directions, including one that seems to defy logic by pointing sunward. 3I Atlas displayed this phenomenon beautifully during October 2025 as it passed perihelion. The images captured by amateur and professional astronomers showed both the normal gas and dust tail streaming away from the Sun and the anti-tail pointing back along the comet's path. Some interpreted this as evidence of active propulsion, as if the comet were a rocket ship expelling material in both directions. But the explanation is purely geometric and optical, a fascinating consequence of viewing angle rather than unusual activity. Similar anti-tails have been observed in dozens of solar system comets under the right geometric conditions, a testament to the tricks of cosmic perspective. The size of 3I Atlas has also been a subject of discussion though, with significant uncertainty. Estimating the size of a comet nucleus is notoriously difficult, because what we primarily see is the coma, the vast cloud of gas and dust surrounding the solid nucleus, which can be thousands of times larger than the nucleus itself. Based on its observed brightness and the estimated reflectivity albedo of its surface, astronomers estimate the nucleus of 3 Atlas is somewhere between 1 and 3 kilometers in diameter. That's substantial, comparable to many long-period comets from our own Oort cloud, but certainly not extraordinarily large. The uncertainty in this estimate is considerable, because we don't know the exact reflectivity of the surface. If the surface is very dark, the nucleus could be larger than estimated. If it's more reflective, it could be smaller. What makes this size estimate particularly interesting is what it implies about the mass and longevity of 3I Atlas. A nucleus several kilometers across contains enough ice and rock to survive many perihelion passages in a solar system, or in this case to retain substantial volatile material even after millions of years spent in interstellar space. The object we're observing isn't a tiny fragment, but a substantial comet that represents a significant sample of material from its parent system. Whatever chemical and isotopic signatures it carries in quantity, making it an incredibly valuable target for detailed study. Despite the challenges of observing a fast-moving interstellar visitor, the rotation state of 3I Atlas adds another layer of complexity. Observations of its light curve, the way the comet's brightness varies over time, suggest it's tumbling rather than rotating smoothly around a single stable axis. This complex chaotic tumbling motion is common in comets and asteroids that have undergone violent collisions or close gravitational encounters that transferred angular momentum in irregular ways. For 3I Atlas, this tumbling could be the direct result of its turbulent ejection from its parent system, possibly through a close gravitational encounter with a giant planet or another massive comet that not only sent it careening into interstellar space, but also set it spinning in an irregular, chaotic manner. Alternatively, the tumbling could have developed more gradually during its millions of years in space due to asymmetric outgassing torques, where jets of gas erupting from the surface exert forces that subtly alter the object's rotation over vast timescales. All of these unusual features, the high speed, the compositional differences, the erratic brightness variations, the anti-tail, the size, uncertainty, the tumbling rotation, each one by itself might seem curious. Together they paint a rich, complex picture of a comet that's been through an extraordinary epic journey. But nothing about these features requires explanation beyond natural processes. Everything we observe is perfectly consistent with a comet that formed in another stellar system, was violently ejected through natural gravitational dynamics, travelled through the cold, silent darkness of interstellar space for eons, and is now purely by chance passing through our solar system, where we have the rare privilege of observing it up close. The anomalies aren't evidence of artificiality, they are evidence of an alien origin. Alien in the truest scientific sense of meaning, foreign from somewhere else, carrying priceless information about conditions and processes in a part of the galaxy we can never directly visit. And that profound realization shifts how we should think about 3I Atlas. This isn't just another comet, it's a natural sample return mission that we didn't have to launch an incredible scientific opportunity that arrived on our doorstep carrying data about another stellar system encoded in its very composition and behaviour. To fully appreciate this unprecedented opportunity, we need to understand the timeline of observations, the sequence of painstaking discoveries that built our current understanding, and the remarkable precision with which astronomers track this fleeting, precious visitor through our cosmic neighbourhood. Let me take you through the journey of discovery, the meticulous sequence of observations that transformed 3I Atlas from a faint moving point of light into one of the most scientifically valuable objects astronomers have studied in years. Because this isn't just a story about detecting a signal, it's a story about human persistence, about the global network of telescopes and observers that came together in an unprecedented effort to track this visitor, and about the narrow, fleeting window of opportunity that made any of this possible. The initial detection of 3I Atlas happened months before the critical radio signal discovery. Automated survey telescopes tirelessly scanning the night sky for near-Earth objects and potential threats flagged an unusual moving object, with a trajectory that simply didn't match anything in the vast catalogue of known solar system objects. Preliminary orbital calculations immediately showed a hyperbolic trajectory, raising intense interest because such orbits are the unequivocal signature of an object not gravitationally bound to the Sun, indicating it was potentially an interstellar visitor. But orbital calculations from early observations always carry a degree of uncertainty, and astronomers needed more data to confirm whether this was truly from beyond our solar system, or just an unusual solar system comet on a very elongated orbit that merely looked hyperbolic. Follow-up observations came quickly, a global scramble for telescope time. Telescopes around the world, from the Canary Islands to Hawaii, targeted the object, measuring its position with increasing precision as it moved against the background stars. Each new measurement refined the orbital calculations, steadily reducing the uncertainty and strengthening the case that this was indeed interstellar. Within weeks, the classification was confirmed: 3 Atlas, the third interstellar object ever discovered, and only the second confirmed interstellar comet after 2E Borisov. The discovery sparked immediate intense interest, because it offered a chance to study an object from another stellar system with far more advance notice than we had with Oumuamua, which was already on its way out of the inner solar system when it was discovered. As 3 Atlas moved inward toward the Sun through the late summer and early autumn of 2025, observatories initiated coordinated monitoring campaigns of unprecedented scale. Optical telescopes tracked its brightness and measured its spectrum, analysing the sunlight reflecting off its surface and the light emitted by gases in its coma. These observations quickly detected water vapour, carbon dioxide, carbon monoxide, and various other volatile molecules typical of cometary outgassing. The spectrum even showed complex organic compounds, likely carbon-based molecules that form in cold radiation-exposed environments. Everything pointed strongly to a comet, but its interstellar origin meant every single detail, every spectral line was scientifically precious a clue to an alien world. By mid-October 2025, 3I Atlas was rapidly approaching perihelion, its closest point to the Sun, at a distance roughly equivalent to Earth's orbit. This is when cometary activity typically peaks, when solar heating is most intense and outgassing reaches its maximum rates. Astronomers knew this would be their single best chance to study the object in detail before it began its long, lonely journey back out into the outer solar system and eventually beyond. Telescopes were booked months in advance. Observation schedules were carefully coordinated to maximise coverage across different wavelengths and with different instruments. The Meerkat Radio Telescope in South Africa, with its 64 individual dishes working together as a single incredibly powerful array, was specifically brought into the observation campaign to search for hydroxyl emissions. Previous interstellar visitors hadn't been studied with this level of radioastronomical scrutiny, partly because the most sensitive telescopes weren't always available, and partly because the objects weren't active enough to produce detectable radio emissions. But with 3I Atlas showing robust outgassing in optical observations, the conditions seemed perfectly right for a radio detection, provided the comet contained sufficient water ice. The pivotal detection came during observations in late October 2025, coinciding almost perfectly with the perihelion passage. Meerkat detected the characteristic 18 centimetre emission of hydroxyl radicals at the expected frequency. The signal strength indicated substantial water outgassing, with early estimates suggesting thousands of kilograms of water were being released per second as the Sun's intense heat drove sublimation across the nucleus's surface. This was the breakthrough, the first confirmed radio detection of an interstellar comet, and it provided invaluable data that optical observations alone could never capture, direct proof of its internal chemistry. What made the radio detection particularly valuable was its ability to measure the outgassing rate directly and precisely. Optical observations can see the glowing coma, but translating that visible brightness into an actual mass loss rate requires complex assumptions about dust-to-gas ratios, particle sizes, and surface reflectivity, all of which introduce significant uncertainties. Radio observations of hydroxyl emission, however, provide a much more direct and robust measurement because the emission intensity is directly proportional to the number of hydroxyl molecules, which in turn is directly related to the water production rate through known photodissociation physics. The Meerkat data gave astronomers their first truly reliable measurement of precisely how much material 3I Atlas was losing as it passed perihelion, a fundamental parameter for understanding its evolution. Simultaneously, optical telescopes were capturing breathtaking images of the comet's coma and tails. The images showed the classic structure of an active comet, a bright central condensation where the nucleus was surrounded by dense gas and dust, a broad coma extending hundreds of thousands of kilometers into space, and twin tails streaming behind as the comet moved through the solar system. The gas tail, ionized by solar radiation and shaped by the solar wind's magnetic fields, appeared ethereal blue in color-filtered images. The dust tail, composed of larger particles gently pushed by radiation pressure, showed a yellow-white color from reflected sunlight. and the anti-tail, that fascinating optical illusion I mentioned earlier, appeared as a distinctive spike pointing back along the orbital path, adding to the visual spectacle. In early November 2025, as 3I Atlas passed perihelion and began receding from the Sun, moving outward, the outgassing started its predictable decline. The hydroxyl emission detected by radio telescopes progressively weakened, following the expected pattern as solar heating decreased. Optical brightness also began to fade, though not entirely uniformly. Several minor outbursts occurred post-perihelion, brief surges in brightness, suggesting structural changes in the nucleus or the exposure of fresh volatile ice as surface layers eroded. These outbursts are common in comets that have undergone intense heating, as thermal stress cracks the surface and allows buried volatile ices to suddenly escape. Throughout this critical period, amateur astronomers played a truly crucial role in the global observation campaign, with telescopes ranging from sophisticated backyard setups to dedicated amateur observatories. Enthusiasts around the world captured countless images of 3I Atlas and submitted them to international databases where professional astronomers could access them. This distributed observation network provided nearly continuous coverage, compensating for gaps in professional telescope schedules and for the fact that any given observatory can only see the object when it's above the horizon and the sky is sufficiently dark. The combined amateur and professional effort created a remarkably complete observational record of the comet's behaviour, through its perihelion passage a testament to collaborative science. By mid-November 2025, 3I Atlas was moving outward past Earth's orbit and heading inexorably toward the outer solar system. The hydroxyl emission was still detectable, but rapidly weakening. The coma was visibly shrinking as outgassing declined in the reduced solar heating. The precious window for detailed observation was inexorably closing. Telescopes began to shift focus to other targets, though monitoring continued at lower intensity to track any unexpected behaviour as the comet slowly cooled. Looking at the complete timeline, what strikes me most is how much we learned in such a remarkably brief window. From its initial detection to its perihelion passage, and beyond the intensive observation period spanned only a few short months. Yet in that time, astronomers gathered data across the entire electromagnetic spectrum from X-rays to radio waves, captured thousands of images, measured chemical compositions with unprecedented detail, tracked structural changes, and achieved the first radio detection of an interstellar comet. The coordination, the dedication, the sheer scientific effort invested in this one object reflects its extraordinary value as a messenger from beyond our solar system, and the data collection isn't entirely over. As 3I Atlas continues its outward journey, moving farther from the Sun and gradually fading from view, telescopes will continue tracking it for as long as humanly possible. Every additional measurement extends our knowledge. Every observation provides more context for understanding this remarkable visitor. But the peak has passed. The most active phase, the phase that produced the hydroxyl signal, and the rich data set we're now analysing that phase, is behind us. What remains is the painstaking interpretation, the rigorous analysis, and the extraction of every possible insight from the observations we managed to capture. And those insights are profound. They reach far beyond just understanding one comet. They touch on fundamental questions about how planetary systems form across the galaxy, how material is transported between star systems, how chemistry evolves in the cold depths of space, and what we can learn about the vast sprawling galaxy simply by studying the tiny objects that drift through it. That's what makes 3I Atlas so important, and that's why we need to carefully consider what this discovery truly means for our broader understanding of the universe and our place within it. The implications of the 3I Atlas radio detection ripple outward far beyond this single icy object. We are standing at the threshold of a new era in astronomy, a profound shift in our cosmic perspective. An era where interstellar visitors are no longer just rare, perplexing surprises, but rather regular, anticipated opportunities for deep scientific investigation. and the methods we've developed and validated to study 3I Atlas, particularly the direct radio detection of hydroxyl emissions, provide a clear blueprint for how we'll study future visitors. Let me explain why this matters so much, why this discovery represents a true turning point in our ability to understand the universe beyond our immediate cosmic neighbourhood. First, consider what 3I Atlas tells us about comet formation in other stellar systems. The fact that this object looks, acts and emits radio signals remarkably similar to comets from our own Oort cloud suggests that the fundamental processes forming comets are universal, or at least astonishingly similar, across vastly different stellar environments. This shouldn't entirely surprise us on one level. The physics of ice formation and the chemistry of protoplanetary disks should in principle follow the same universal laws everywhere. But confirmation matters profoundly in science. Seeing those universal processes reflected in an actual tangible object that originated from another star system transforms theoretical expectation into undeniable observational fact. The hydroxyl detection specifically tells us that water ice is abundant in 3I Atlas, and by extension likely common in comets from other stellar systems. Water, as we know, is one of the most fundamental molecules for life, as we know it, a ubiquitous solvent and chemical reactant. Finding it in abundance in an interstellar comet suggests that the chemical building blocks of life, or at least the raw materials that could potentially support life, are distributed widely throughout the galaxy. This doesn't mean life is common, or that 3I Atlas carried living organisms. It means the universe is chemically rich and diverse, and the molecules essential for biology aren't rare or confined to a few special locations. The high carbon dioxide content offers another invaluable clue about formation conditions in its parent solar system. The precise ratio of carbon dioxide to water ice in comets varies depending on where and when they formed within their stellar nursery. Comets that formed farther from the Sun in colder regions tend to have more carbon dioxide and other volatile ices. The relatively high CO2 content in 3I Atlas might therefore indicate it formed in the particularly cold outer regions of its parent system, or that the overall temperature conditions in that system's protoplanetary disk were generally colder than in ours. These are the kinds of profound comparative insights we can only gain by studying objects from different stellar systems, unlocking the diverse histories of star formation across the cosmos. But the implications go beyond just chemistry. The very fact that we have now confirmed 3 interstellar objects passing through our solar system in just a few recent years tells us something fundamental about the population density of interstellar material. If we're detecting a few objects per year with our current survey capabilities, and considering that we can only detect objects that pass close enough and are bright enough to spot, the total number of interstellar objects passing through our vicinity must be enormous, almost incomprehensible. Estimates based on these few detections suggest there could be thousands or even millions of interstellar objects within our solar system at any given time, most too small, too dark, or too distant to detect with current technology. This profound realization reframes how we think about our solar system's boundaries. The traditional picture of the solar system as a neat, isolated collection of planets orbiting the Sun with a firm boundary somewhere beyond Neptune or in the distant Oort cloud is incomplete. In reality, our solar system is constantly being visited by material from elsewhere, a constant subtle influx of interstellar matter passing through occasionally close enough for us to detect. We are not isolated. We are part of a grander galactic ecosystem where material continually circulates and mixes between star systems carried by the gentle gravitational currents and perturbations of the galaxy itself. The radio detection method, so powerfully validated with 3I Atlas, opens entirely new possibilities for detecting and characterizing future interstellar comets. Radio telescopes can observe objects in conditions where optical telescopes struggle, such as during daylight hours or when the object is very close to the Sun, shining too brightly for visible light. From our perspective, radio observations also provide direct, unambiguous data about composition and activity that optical observations can't easily capture. As radio telescope technology continues to improve with arrays like Meerkat, already pushing boundaries, and the upcoming Square Kilometre Array SKA coming online, with unprecedented sensitivity, we'll be able to detect hydroxyl emissions from fainter, more distant objects, vastly expanding our ability to study interstellar visitors. There's also an exciting possibility that 3i Atlas represents a type of object we'll see more of as our detection capabilities improve: long-period comets from our own Oort cloud. Objects with orbital periods of thousands or millions of years are thought to be pristine samples of material from the early solar system, largely unchanged since they formed. But they've still spent their entire existence within the Sun's gravitational influence, subject to occasional perturbations from passing stars or giant molecular clouds that alter their orbits. Interstellar comets like 3i Atlas, however, have potentially spent millions, even billions of years in true interstellar space, isolated from any star's direct influence, preserved at temperatures near absolute zero. This makes them even more pristine, almost perfectly preserved samples of protoplanetary disk material from another star system, a cosmic time capsule unlike any other. The age of 3i Atlas is particularly intriguing. We can't measure its age directly, but we can infer constraints. If the comet has been travelling through interstellar space for millions of years at its observed velocity, it has covered distances of tens or hundreds of light years. The stellar system where it formed might have been much closer to our solar system when the comet was ejected, and galactic rotation has since carried that system to a completely different region of the galaxy. Alternatively, the comet might have been ejected from a system that's now far away, and its long, improbable journey brought it by chance into our neighbourhood. Either way, we're observing an object that's potentially older than some of the surface features on Earth, a piece of cosmic history frozen in time and delivered to our doorstep. The implications extend profoundly to our understanding of how material and, by extension, information might spread through the galaxy. If interstellar comets are common, and if they occasionally get captured into orbit around stars rather than just passing through, they represent a powerful mechanism for transferring material between stellar systems. A comet ejected from one system carrying ice and complex organic molecules formed in that system's protoplanetary disk could be captured by another system millions of years later, delivering those molecules to a completely different environment. This process, termed lithopanspermia at its most extreme, has even been proposed as a potential mechanism for spreading life or its precursors between star systems. I'm not suggesting 3i Atlas is carrying life. The chances of any biological material surviving the cold, the radiation and the vacuum of interstellar space for millions of years are essentially zero. But complex organic molecules, the chemical building blocks that life uses, could potentially survive such journeys, and if comets like 3i Atlas are regularly travelling between star systems, they are effectively mixing and distributing those organic molecules across the galaxy, potentially influencing the chemistry of planetary systems they visit or get captured by. The galaxy then becomes not just a collection of isolated stellar systems, but a connected, vibrant chemical network where material circulates and interacts over vast timescales. The discovery also highlights critical gaps in our current knowledge and capabilities. We detected 3i Atlas relatively close to perihelion, which gave us a good observing window, but it also meant we missed the chance to study it during its approach through the outer solar system, when it was cold and inactive, a truly pristine dormant state. Future detection systems, particularly the Vera Rubin Observatory's Legacy Survey of Space and Time LSST, which will begin operations in the coming years, are expected to detect interstellar objects much earlier, potentially giving us months or even years of advance notice. That advance warning would allow us to plan dedicated observation campaigns and possibly even direct spacecraft missions to intercept and study these visitors up close. Imagine what we could learn from a spacecraft mission to an interstellar comet. We could sample the ice directly measuring isotopic ratios that reveal exquisite details about the temperature and chemistry of the protoplanetary disk where it formed. We could analyse complex organic molecules with laboratory instruments far more sensitive than any telescope can provide. We could image the nuclear structure, understand its composition layer by layer, and directly test theories about how comets form and evolve. Several mission concepts have been proposed for intercepting interstellar visitors, though none have been funded yet. But 3i Atlas and objects like it make the scientific case for such missions increasingly compelling and urgent. The radio detection also powerfully demonstrates that we don't need to wait for dedicated space missions to learn profoundly from interstellar visitors. Ground-based observatories, with increasingly sophisticated instruments and coordinated observation strategies, can extract enormous amounts of information from these fleeting encounters. The key is meticulous preparation, having observation plans ready, having telescope time allocated across a global network, and fostering the international coordination to maximise coverage. The success with 3i Atlas shows that this approach works, that we can mobilise the global astronomical community to focus on these rare opportunities and generate high-quality scientific returns. Yet even as we celebrate what we've learned, I'm acutely aware of how much remains unknown. Every answer we gain raises new questions. Every measurement reveals gaps in our understanding. And that's precisely what makes this field so exciting, so dynamic, so full of potential for future discovery. The study of interstellar objects is still in its infancy, with only 3 confirmed examples and limited, albeit precious, data on each. But the trajectory is clear. As our detection capabilities improve, as our instruments become more sensitive, as our theoretical understanding deepens, we'll detect more of these visitors, study them in greater detail, and gradually build a comprehensive picture of the interstellar population. 3i Atlas is a monumental milestone on that journey, not the destination. And the questions it leaves unanswered are perhaps even more valuable than the questions it resolved. They are the seeds of future discoveries. Let's talk about what we don't know, because for all the data we've collected, for all the insights we've gained, 3i Atlas remains in many ways a mystery wrapped in ancient ice and primordial rock. A traveller from an unknown origin carrying secrets we've only begun to uncover. And acknowledging these gaps in our knowledge isn't a weakness. It's precisely how science progresses. It's how we identify where to focus future efforts, what instruments to build, and what questions matter most. So let me walk you through the enduring mysteries that keep astronomers awake at night, the puzzles that 3i Atlas presents even after months of intensive study. The most fundamental unanswered question is, where exactly did 3i Atlas come from? We can meticulously backtrack its trajectory and determine its general direction of origin, somewhere in the direction of the constellation Draco. But that doesn't identify a specific parent star. The challenge is immense because the comet has likely been travelling for so long, millions of years, that the star system where it formed has moved significantly due to the complex gravitational dance of galactic rotation and its own proper motion through space. Even if we knew the exact direction the comet came from when it entered our solar system, tracing that line back millions of years requires accounting for the complex, ever-changing gravitational dynamics of the galaxy. The subtle perturbations from countless passing stars and inherent uncertainties in the comet's trajectory before it encountered our Sun. The parent star could now be anywhere within a vast volume of space hundreds of light years across. Some researchers are attempting to narrow down candidates by looking at the comet's composition and comparing it to theoretical models of stellar systems with different properties. For example, if we could measure the deuterium to hydrogen ratio DH in the water ice, a sort of cosmic thermometer that would tell us about the temperature conditions when the ice formed, which correlates with distance from its parent star. If we could measure other isotopic ratios like oxygen 18 to oxygen 16, or carbon 13 to carbon 12, we could further constrain the chemical evolution of the proto-Lanitre disk. But these measurements require spectroscopic precision that's incredibly challenging to achieve with a fast-moving distant object, especially now that 3i Atlas is receding and fading. Another persistent mystery is how 3i Atlas was ejected from its parent system in the first place. gravitational interactions with giant planets can violently kick comets into the outer reaches of a stellar system or even eject them into interstellar space entirely. This chaotic process is probably how most interstellar comets form, but the specific dynamics matter because they determine the precise velocity and direction of ejection, which in turn affects where the comet ends up millions of years later. Was 3I Atlas ejected during the turbulent formation phase of its stellar system when planets were still migrating chaotically and gravitational interactions were frequent and violent, or was it ejected later by a close encounter with a rogue planet, or during a stellar flyby where another star passed too close? We simply don't know the exact mechanism, and without knowing where it came from and how it was ejected, we can't fully reconstruct its ancient history. The internal structure of 3I Atlas also remains largely unknown. We've observed the surface and the expansive coma, but what lies beneath that icy crust is the nucleus relatively homogeneous, a uniform mixture of ice and rock throughout, like a simple snowball, or is it layered with different compositions at different depths reflecting the changing conditions during its formation? Does it have large voids, pockets of weakness that could cause it to fragment if heated too intensely? The unpredictable outbursts we observed certainly suggest structural heterogeneity with uneven distribution of volatiles. But we can't image the interior with current technology. Understanding internal structure matters immensely because it affects how the comet responds to solar heating, how it outgasses, and ultimately how long it can survive as a coherent object. The rotation state and its evolution add another layer of mystery. We know 3I Atlas is tumbling, but the precise rotation period and axis orientation are uncertain and likely complex. Moreover, outgassing itself creates torques that can subtly alter a comet's rotation over time, potentially causing it to spin faster, slower, or change its axis orientation. For 3I Atlas, these outgassing torques are particularly interesting because they're asymmetric, varying as different parts of the nucleus are heated. Over the months of its perihelion passage did the rotation state measurably change. If we could precisely measure that change, it would tell us invaluable information about the distribution of active areas on the surface, the efficiency of outgassing from different regions, and the nucleus's overall response to thermal stress. There's also the fundamental question of how pristine 3I Atlas really is. I've mentioned that interstellar objects are potentially more pristine than solar system comets because they've been isolated in the cold vacuum of space for so long, but pristine doesn't mean unchanged. Interstellar space isn't perfectly empty. It contains diffuse gas, microscopic dust, and high-energy cosmic rays. Over millions of years, even a small flux of these particles can subtly alter surface chemistry, breaking down complex molecules, sputtering away material, or creating entirely new compounds through radiation chemistry. How much has the surface of 3I Atlas been processed, weathered, by its long interstellar journey? Does the surface composition still accurately reflect its formation environment, or has it been modified into something new, something unique to interstellar exposure? The hydroxyl detection answered questions, but it invariably raised others. The emission intensity gives us the total water production rate, but it doesn't tell us about the detailed distribution of water ice within the nucleus. Is the ice concentrated in certain regions, perhaps buried deep? Is it mixed uniformly with dust and rock? The fact that we detected hydroxyl at all confirms substantial water content, but the detailed spatial distribution of that water affects how we interpret the observations and what we can infer about its formation conditions. Future radio observations with higher angular resolution might be able to map the hydroxyl emission across the coma, revealing which parts of the nucleus are most active. But for 3I Atlas, we don't currently have that level of spatial detail. Another intriguing question is whether 3I Atlas has visited other stellar systems before ours. An object travelling through interstellar space for millions of years at 15 kilometers per second could cover significant distances, potentially passing near other stars along its journey. If it did those close encounters alter its trajectory or cause brief heating episodes that modified its surface? Some simulations suggest that close stellar passages could temporarily activate outgassing, even in interstellar space. If the star is luminous enough and the approach close enough, any such event would be brief, but it could leave subtle signatures in the surface structure or composition that we might detect if we knew what to look for. The ultimate fate of 3I Atlas is also uncertain in some ways. We know it's on a hyperbolic trajectory that will carry it back out of the solar system never to return. But where will it go next? Its velocity and direction after exiting our system will determine precisely which region of the galaxy it travels through next, whether it might encounter another star system in the foreseeable cosmic future, and ultimately where it will be when our sun runs out of fuel, billions of years from now. Backtracking the trajectory is hard. Projecting forward is even harder because we can't predict the subtle gravitational perturbations it will experience from unseen rogue planets, brown dwarfs, or distant stellar encounters along its vast unknown path. I'm also fascinated by what we didn't detect. Throughout the entire observation campaign, astronomers were acutely alert for any unusual emissions, any unexpected signals that might indicate composition or activity we haven't seen before. But everything detected, every spectral line, every emission, fell squarely within the range of what we've observed from solar system comets. Does that mean interstellar comets are in fact largely indistinguishable from our own in their fundamental chemistry? Or does it simply mean our instruments aren't yet sensitive enough to detect the subtle, perhaps exotic differences that truly define their alien origin? We can only measure what our technology allows, and there might be chemical or physical properties of 3I Atlas that remain hidden, simply because we don't have the right tools to see them yet. The comparative study of interstellar objects is still severely limited by its small sample size. We've only confirmed 3 Oumuamua 2I Borisov and now 3 Atlas. That's simply not enough to draw broad, statistically robust conclusions about the diversity of interstellar populations. Are these 3 representative of typical interstellar objects, or are they rare outliers that just happen to be detectable? We won't know until we've studied dozens or even hundreds of interstellar visitors, and that will take years or decades of continued surveys and observations. Every new detection will either confirm existing patterns or reveal surprising new diversity, gradually building our understanding of what's typical and what's truly unusual. There's also a meta question about observation strategy. Did we study 3I Atlas optimally? Or in hindsight, would different choices have yielded even more valuable data? Should more telescope time have been allocated to radio observations versus optical or vice versa? Should we have prioritized spectroscopy over imaging or focused on different wavelengths? These aren't criticisms. They're honest scientific reflections on how we allocate limited resources when studying rare, fleeting opportunities. Every interstellar object detection is a crucial learning experience that informs how we approach the next one, gradually refining our methods and priorities. And finally, there's the biggest question of all: what will the next interstellar visitor reveal? Will it be similar to 3I Atlas, reinforcing existing patterns and confirming theories? Or will it be radically different, perhaps like Oumuamua, forcing us to reconsider our fundamental assumptions about what interstellar objects can be? The universe has a habit of surprising us, of presenting phenomena we didn't predict or anticipate. Staying open to those surprises while rigorously maintaining scientific skepticism is the constant challenge we face with every new discovery. These unanswered questions aren't frustrations, they're invitations. They're doorways to future research, to new observations, to deeper understanding. And they remind us that science is a process, an endless journey of exploration, not a destination. We don't study interstellar objects to close the book on cosmic mysteries. We study them to open new chapters, to ask better, more incisive questions, to push the boundaries of what we know further into the vast unknown territory of what we have yet to discover. And in that context, 3I Atlas isn't an endpoint. It's a beginning, a breathtaking glimpse of the richness and diversity that awaits us as we continue exploring the objects that wander through our solar system, carrying messages from distant, unseen corners of the galaxy. To truly appreciate 3I Atlas, we need to zoom out and see it as part of a larger evolving story. A story about humanity's growing awareness that our solar system isn't a closed, isolated system, but rather a dynamic waypoint in a galaxy filled with wandering objects. Let me take you through the brief but profound history of interstellar object detection and place 3I Atlas in the context of what came before and what might come after. Because this isn't just about one comet. This is about recognizing that the universe is far more dynamic, far more interconnected, and far more awe-inspiring than we once imagined. The story begins with Oumuamua, the first confirmed interstellar object detected in October 2017 by the Pan-STARRS telescope in Hawaii. The name means scout or messenger in Hawaiian, and it lived up to that name by completely upending our assumptions about what interstellar visitors would look like. Oumuamua's trajectory was clearly hyperbolic, proving beyond doubt that it came from outside our solar system. But everything else about it was puzzling, almost infuriatingly ambiguous. Its shape appeared extremely elongated, like a cigar, or perhaps a pancake based on how its brightness varied dramatically as it rotated. Its surface was unusually reflective, and most mysteriously its trajectory showed a slight unexplained acceleration that couldn't be accounted for by solar gravity alone. That acceleration sparked intense, often heated debate. Some astronomers proposed that Oumuamua was indeed experiencing outgassing, releasing jets of material that created a tiny rocket effect similar to how comets accelerate. But critically, no coma or tail was detected, no clear visible evidence of the outgassing that typically accompanies such acceleration. Others, including some respected scientists, suggested more exotic explanations: a light sail pushed by solar radiation pressure, a fragment of a Dyson sphere, even an extraterrestrial probe. While most scientists favoured natural explanations, proposing that Oumuamua might be composed of unusual invisible materials like solid hydrogen or nitrogen ice that would outgas without a visible coma, the lack of definitive, unambiguous data left ample room for tantalising speculation. What Oumuamua taught us more than anything was that we weren't prepared. The object was detected only after it had already passed perihelion and was rapidly heading back out of the solar system. We had only a few precious weeks to observe it before it faded beyond detection capabilities, and in that brief window we simply couldn't gather enough data to resolve all the profound mysteries it presented. The experience was humbling but immensely educational. It motivated immediate efforts to dramatically improve our detection capabilities and develop faster, more coordinated response protocols for studying interstellar visitors before they slip away forever. 2 years later, in August 2019, amateur astronomer Gennady Borisov discovered the second interstellar object subsequently designated 2I Borisov. Unlike Oumuamua, there was no ambiguity about what 2I Borisov was. It showed clear, undeniable cometary activity from the moment of discovery with a visible coma and tail. Its spectrum revealed abundant water vapor, carbon monoxide, and other molecules typical of solar system comets. It behaved exactly like a comet should, following predictable patterns of brightness increase as it approached the sun and decrease as it receded. In many ways, 2I Borisov was profoundly reassuring because it fit our expectations, confirming that at least some interstellar objects are straightforward, unremarkable comets that happen to have wandered in from elsewhere. The detection of 2I Borisov several months before its perihelion gave astronomers a precious advantage time. They could plan comprehensive observation campaigns, coordinate between different telescopes and instruments across the globe, and track the comet's evolution through its entire passage. The data collected from 2I Borisov was far more comprehensive than what we managed with Oumuamua, and it provided the first detailed chemical analysis of an interstellar comet. Surprisingly, the overall composition of 2I Borisov was quite similar to many solar system comets, again suggesting that fundamental comet formation processes might be relatively universal across different stellar systems. But 2I Borisov also showed some subtle, distinctive features. Its carbon monoxide to water ratio was higher than typical solar system comets, and its structure seemed unusually compact and dense. These differences hinted at formation in a colder environment or around a different type of star. The observations demonstrated that even though interstellar comets might look similar to our own, at first glance detailed study reveals subtle variations that encode invaluable information about their diverse origins. Now with 3i Atlas we have a third crucial data point, and the emerging pattern is becoming clearer. Interstellar objects aren't all exotic, ambiguous mysteries like Oumuamua. Some, perhaps most, are comets showing normal cometary behaviour, distinguishable from solar system objects only by their hyperbolic trajectories and possibly subtle compositional differences. The hydroxyl detection from 3i Atlas powerfully reinforces this pattern. It's a comet. It outgasses. It follows known physics. But it carries profound chemical information about another stellar system, making it scientifically invaluable despite its mundane behaviour. Comparing the three objects is highly instructive. Oumuamua remains largely an enigma. Its unusual acceleration and lack of clear outgassing are still not fully explained despite numerous proposed theories. 2i Borisov was unambiguously a normal comet, active and well behaved. 3i Atlas falls somewhere in between, showing normal cometary activity, but with intriguing, slightly unusual characteristics like its high carbon dioxide content and somewhat erratic brightness variations that make it deeply interesting, even though it's clearly natural. This diversity, even from just 3 examples, suggests that the interstellar population is varied, including objects that formed under different conditions, evolved along different paths, and present different observational challenges. Beyond these 3 confirmed interstellar objects, there have been tantalizing hints and false alarms. Various objects detected by survey telescopes initially showed orbital parameters suggesting possible interstellar origin, only to be reclassified as solar system objects after more data refined their trajectories. The challenge is immense because accurately determining whether an orbit is truly hyperbolic requires very precise measurements, especially for objects that come from the outer solar system and have velocities extremely close to the threshold between bound and unbound orbits. As our detection capabilities continue to improve, we'll likely see more candidate interstellar objects that turn out to be borderline cases or require extensive coordinated observation to definitively confirm their nature. There's also the crucial question of how many interstellar objects we're currently missing. Current detection systems are inherently biased toward objects that are relatively large, bright and pass close enough to Earth. Smaller objects, darker objects, or those that stay farther out in the solar system could easily escape detection entirely. Statistical models based on the objects we've detected suggest there might be several interstellar visitors per year passing through the inner solar system, and potentially thousands if you count the entire volume out to Neptune's orbit. Most go utterly unnoticed, invisible messengers carrying priceless information we never receive simply because we're not looking in the right direction at the right time. The comparison with SETI signals is worth exploring too. When we talk about receiving a signal from 3i Atlas, we're using language that echoes SETI, the search for extraterrestrial intelligence, which has been scanning the skies for artificial radio transmissions from alien civilizations for decades. SETI has detected numerous candidate signals over the years, brief strong radio emissions that stood out from background noise and momentarily raised hopes of first contact. But everyone has either failed to repeat when telescopes were pointed back at the source, or was eventually traced to terrestrial interference or natural astrophysical phenomena. The hydroxyl signal from 3i Atlas is fundamentally different. It's not a candidate signal waiting for confirmation. It's a verified natural emission with a well-understood physical origin. But the emotional arc of discovery is similar. The excitement of detection, the initial speculation about meaning, and ultimately the profound satisfaction of understanding. What SETI teaches us is the paramount importance of scientific rigour, of not jumping to conclusions, of carefully evaluating all plausible explanations before accepting extraordinary claims, and that same rigorous skepticism applies equally to studying interstellar objects. Yes, they're from beyond our solar system, which is inherently exciting. But excitement doesn't justify abandoning careful evidence-based analysis or embracing unsupported theories. The field of interstellar object studies is also profoundly benefiting from advances in related areas of astronomy. The study of exoplanets, planets orbiting other stars, has exploded over the past 2 decades with thousands of confirmed detections and increasingly sophisticated methods for characterizing their properties. Some of those same methods, particularly spectroscopy and photometry, apply directly to studying interstellar objects. And the discoveries about exoplanetary systems revealing incredible diversity in planet types, orbital configurations and system architectures inform our expectations about the interstellar objects that might be ejected from those systems. Similarly, the study of protoplanetary disks, the rotating clouds of gas and dust around young stars where planets form, has advanced dramatically with powerful telescopes like ALMA Atacama Large Millimeter Submillimeter Array that can image these disks in unprecedented detail. We can now see the intricate structure within these disks, the gaps and rings carved by forming planets, the distribution of different molecules at different temperatures and distances from the star. This profound knowledge provides invaluable context for interpreting the composition of interstellar objects. When we detect high carbon dioxide in 3I Atlas, we can compare that to observations of CO2 in protoplanetary disks and infer where in a disk such a comet might have formed. The next frontier in interstellar object studies is likely to involve direct spacecraft missions. Several ambitious mission concepts have been proposed over the years, including small fast probes that could be launched to intercept an interstellar object and conduct close-up observations or even land on its surface. The technological challenges are substantial, primarily because interstellar objects move incredibly fast and often aren't detected until they're already close to perihelion, leaving little time to launch an intercept mission. But these challenges aren't insurmountable, especially if we develop spacecraft that can be launched quickly and economically, or if future detection systems give us years of advance warning. Imagine what a spacecraft could discover. It could image the nucleus at incredibly high resolution, seeing details that ground-based telescopes can't possibly resolve. It could sample the coma, directly analysing the gas and dust, with laboratory instruments far more sensitive and diverse than remote observations allow. It could measure isotopic ratios with exquisite precision, revealing the exact temperature and chemical conditions when the comet formed. It could even potentially return samples to Earth, bringing material from another stellar system directly into our laboratories, where scientists could study it with every single tool available. The scientific return from such a mission would be extraordinary, potentially revolutionising our understanding of planetary system formation across the galaxy. But even without dedicated spacecraft missions, the future of interstellar object studies is incredibly bright. Next-generation survey telescopes like the Vera Rubin Observatory will detect interstellar objects earlier and more frequently, providing larger samples and better statistics. Improved radio telescopes like the SKA will allow more sensitive detections of molecular emissions, revealing composition details we can't currently access. And as our theoretical understanding deepens, we'll be better able to interpret the observations, extracting maximum information from every precious data point. The story of interstellar objects is still being written, and we're living through the opening chapters. Every new detection adds another piece to the vast cosmic puzzle, another clue about the true nature of the galaxy we inhabit. 3I Atlas is one pivotal chapter in that story, a particularly valuable one because of the groundbreaking hydroxyl detection and the comprehensive observation campaign, but it's not the last chapter. The universe has more messengers to send our way, more objects carrying information from distant stellar systems, and we're finally developing the tools and the knowledge to read the messages they bring. That profound realization points forward toward a future where studying interstellar visitors becomes routine, where every few months brings a new object to observe and analyze, and where we gradually build a comprehensive picture of the material landscape of our galaxy, understanding its rich dynamic interconnectedness. So where do we go from here? You've followed the journey of 3I Atlas from its mysterious signal detection through the rigorous scientific explanations and into its broader cosmic implications. You understand what this object truly is, what it tells us, and what fascinating mysteries still remain unsolved. But the story doesn't end with understanding. It ends with anticipation, with looking forward to what comes next, with recognizing that 3I Atlas is just one chapter in a much larger narrative that's still unfolding around us. And you're part of that narrative whether you realize it or not. Let me explain why. As 3I Atlas recedes from our solar system, growing fainter with each passing week, astronomers are already preparing for the next interstellar visitor, because there will be a next one. The question isn't if, but when and what form it will take. Based on the 3 confirmed detections, in just a few years we can expect interstellar objects to be discovered relatively regularly, now that survey telescopes are specifically designed and watching for them. Some will be detected early enough for comprehensive multi-year study. Others might slip through barely noticed. But each one, every single one, offers an unparalleled opportunity to expand our understanding, to test theories, and to discover something utterly unexpected about the cosmos. The Vera Rubin Observatory, scheduled to begin its legacy survey of space and time LSST in the near future, will be a revolutionary game-changer for interstellar object detection. With its massive mirror, unparalleled wide field of view and rapid survey cadence, it will meticulously scan the entire visible sky every few nights, detecting faint objects and tracking their motion with unprecedented efficiency. Sophisticated computer algorithms will automatically flag objects with unusual trajectories, including potential interstellar visitors, allowing astronomers to begin follow-up observations within hours or days of initial detection. The early warning that Rubin provides could give us months or even years to study interstellar objects before they reach perihelion and begin their inevitable exit from our solar system. Radio telescope arrays are also continuing their rapid improvement. The Square Kilometre Array, SKA, currently under construction across sites in South Africa and Australia, will be the most sensitive radio telescope ever built when completed. Its ability to detect incredibly faint emissions, including hydroxyl and other molecular lines, will allow astronomers to study outgassing from interstellar comets in far greater detail than was possible with 3I Atlas. We'll be able to map the precise distribution of gas in the Comet track, how outgassing varies with rotation and solar distance, and possibly even detect molecules that are currently below our detection thresholds. Every improvement in instrumentation, every leap in technology opens vast new observational windows onto the universe. But technology alone isn't enough. We also need unparalleled coordination, seamless communication, and a vibrant scientific community. The remarkable success in studying 3I Atlas came directly from the collaboration between professional observatories, dedicated amateur astronomers, and research institutions around the world. That model will become even more critically important as the number of interstellar objects increases. Developing rapid response networks sharing data in real time across continents, and coordinating observation schedules across different time zones and instruments will maximize what we can learn from each fleeting visitor. And the amateur astronomy community plays a truly vital role in this global network, providing continuous monitoring and backup observations that fill crucial gaps in professional telescope schedules. There's also a powerful need for public engagement and education. Interstellar objects capture the human imagination in ways that many astronomical phenomena simply don't. They're tangible, comprehensible, and profoundly mysterious all at once. A comet from another star system is something anyone can understand and wonder about regardless of their scientific background. And that wonder, that innate human curiosity, can translate into invaluable public support for scientific research, for funding telescopes and missions, for encouraging young people to pursue careers in astronomy and planetary science. Every time an interstellar object makes headlines, it's a golden opportunity to communicate science, to explain the rigorous process of discovery, to show how curiosity and diligent investigation truly lead to knowledge. What I want you to take away from the 3i Atlas story isn't just the facts about hydroxyl emissions and cometary outgassing. I want you to understand the mindset, the rigorous evidence-based approach that separates genuine scientific investigation from sensational speculation. It's about following the evidence wherever it leads, even if the destination is less sensational than imagined alien probes. It's about asking good questions and being willing to accept answers that in turn create new, deeper questions. It's about recognizing that nature is often more subtle, more complex, and ultimately more interesting and awe-inspiring than the simple narratives we might prefer. The universe doesn't owe us mysteries that fit our expectations. It doesn't promise alien civilizations or impossible physics or easy answers. What it offers is reality, which is simultaneously more mundane in its components and more profound in its implications than any work of fiction. A comet made of ice and rock travelling between stars for millions of years, preserving within its frozen heart the chemical signature of a stellar system that might no longer exist in any recognisable form, arriving in our neighbourhood purely by chance, just as we've developed the technology to detect it and understand what it is. That's not science fiction, that's science fact, and it's utterly breathtakingly extraordinary. Looking forward, some of the most exciting possibilities involve detecting interstellar objects even earlier in their approach. If we could spot an interstellar comet when it's still beyond Jupiter's orbit, years before perihelion, we'd finally have the precious time needed to plan dedicated spacecraft missions. Engineers have already proposed concepts for fast response probes that could be launched on short notice, use gravitational assists to match velocity with the target, and conduct close-up studies that ground-based telescopes can't achieve. Such missions would be challenging and undoubtedly expensive. But the scientific payoff would be enormous, truly paradigm-shifting, and the technological capabilities required, rapid launch systems and advanced propulsion, have applications far beyond just studying interstellar visitors. There's also the tantalizing possibility of detecting active outgassing from an interstellar object, while it's still far from the Sun, potentially revealing its pristine composition details before the comet is heated and altered by solar radiation. This would require extremely sensitive telescopes and probably some luck in catching the object at just the right moment, but it's not impossible. If we could detect hydroxyl or other molecular emissions from an interstellar comet, while it's still in the outer solar system, we'd be observing truly pristine material, virtually unchanged by any recent heating, providing the most direct look possible at the comet's original primordial composition. Another crucial avenue for future research involves statistical studies of the interstellar object population. As we detect more examples, patterns will inevitably emerge. We'll be able to estimate what fraction are rocky asteroids versus icy comets, what the typical size distribution looks like, whether certain compositions are common or rare, and how these properties might correlate with the regions of the galaxy from which the objects originated. Building this robust statistical picture requires many detections, which means years of patient observation and meticulous data collection. But eventually we'll have enough data to draw robust, confident conclusions about the interstellar population as a whole, not just individual, isolated objects. I'm also fascinated by the potential for detecting very small interstellar objects, particles or pebbles, rather than kilometre-sized comets or asteroids. These tiny travellers are probably far more numerous than large objects, but vastly harder to detect because they're so faint. However, when they enter Earth's atmosphere, they create brilliant meteors, and some sophisticated meteor detection networks are now advanced enough to calculate trajectories that might just reveal an interstellar origin. If we could confirm interstellar meteors and recover fragments as meteorites, we'd have actual physical samples from other stellar systems to study in laboratories here on Earth. The hunt for interstellar meteorites is an emerging subfield that could yield incredible tangible results in the coming years. Ultimately, what's next depends partly on nature and partly on us. Nature will determine what objects pass through our solar system and when. We as humanity determine whether we're looking, whether we have the tools to detect and study them, and whether we're asking the right questions. The story of 3i Atlas shows that we're getting better at all of these things. We detected an interstellar comet, mobilized a global observation campaign, collected comprehensive data across multiple wavelengths, and achieved the first radio detection of hydroxyl emissions from such an object. That's progress, that's success, and it's a strong foundation for doing even better next time. But I'll leave you with this thought. Every one of us looking up at the night sky is seeing light from objects billions of miles away. Photons that travelled through space for minutes, or hours, or years before reaching our eyes. We're already connected to the cosmos in the most direct, visceral way possible. And when we learn about objects like 3i Atlas, when we understand their origins and their epic journeys, we're deepening that connection. We're not just passively observing the universe, we're part of it. Participants in a cosmic story billions of years old, adding our own chapter through curiosity and discovery. 3i Atlas is fading now, moving back into the cold darkness between stars, its brief, brilliant moment of visibility coming to an end. But the invaluable knowledge it gave us remains. The sophisticated methods we developed to study it will be applied to future visitors. The profound questions it raised will drive scientific research for years to come. And somewhere out there, the next messenger is already on its way, travelling through space at kilometres per second, carrying its own unique secrets and surprises. We just need to be ready when it arrives. And based on what we've learned from 3i Atlas, I'm confident we will be. The signal from 3i Atlas wasn't a coded message from alien engineers. It was something far better, far more profound. It was a transmission from the universe itself, speaking in the universal language of chemistry and physics, telling us that we're surrounded by wonders waiting to be understood if only we learn to listen. And that's the real story. The enduring message that matters more than any speculation about probes or beacons. We're living in an age where the universe is revealing itself to us in ways previous generations could only imagine. The question isn't whether there are more mysteries to discover. The question is whether we're paying attention, whether we're willing to look with both insatiable curiosity and rigorous skepticism, and whether we're ready for whatever truth the next cosmic visitor brings. Stay curious, stay skeptical, and keep watching the skies. Because the universe has more to say. And every signal, every detection, every unexpected discovery is an invitation to understand a little more about the vast, ancient, and endlessly fascinating cosmos we call home.